So at the end of class last time, I think this is right, didn't we just do add to end? I'm pretty sure that's right.
We did my reverse.
And we did my reverse using add to end. And so do you remember what, let's take a look here at at our definition of add to end. It's, if the empty list, it takes two parameters, a list and an element, and if the list is empty, then it just conses the element with the empty list. Otherwise, it conses the car of the list with the add to end of the cooter of the list and the element. Remember we looked at that? And do you remember what the big theta of this, the efficiency was, the big theta? Remember we asked you that last time. Remember what that was? Because what does it have to do? How does it actually put it at the end? What does it have to do? It has to call itself recursively how many times? N times. And there's no additional, it just calls itself once. There's only one call to add to end here. And each time it calls it, the list is decreased by 1. So what did we say the big theta of this was? Big theta of what? Oh, come on. Yeah, no, what do you mean a lot? It's big theta of n. Is everybody? Well, yeah, but then the question is, what about the efficiency of my reverse? Because what did my reverse do? It calls add to end. Yes, it called add to end, and each time it calls add to end recursively, it does add to end of a list of n minus 1, of length n minus 1, right? Is that right? Yes, because it's the cooter of the list. So how long is, if the list has length n, then the cooter of the list has length what? N minus 1. And so it calls itself recursively n minus 1 times. But the problem is, each time it calls itself, when it calls itself that n minus 1 times, then the add to end does its thing with that call. And then it calls it with n minus 2, and then the add to end does it with n minus 2. So it's like a loop in a loop in a loop. And so therefore, what was our conclusion is the efficiency of my reverse. Because it was a loop inside of a loop. What was it? It was n squared. Now, is everybody clear on how to reason that out? If you were to do this, if we were to do this formally, we would write the recurrence, and we'd do n minus 1, and we'd solve the recurrence and all that stuff. But for now, I think we can just see this. Yeah. Did you have a question?
Yeah. Does it always suffice to just look at how many times loops are stacked within themselves to see what the order is? It is not the case that every doubly nested loop is order n squared, because it depends on what's controlling the loop. Right. You
see what I mean? If the loop goes down by 1 each time, then that's true. Then it is big theta of n squared. But 99% of the cases, that is in fact what happens. So I would say 99% of the time when you have nested loop and each one of them is big theta of n, it's big theta of n squared. But not necessarily always. Okay? And so, but look, intuitively we ought to be able to reverse the list in time big theta of n, right? Because as all you're doing is taking these elements and just putting them in reverse order. You ought to just be able to go through the list one time and have them reversed. Go through it one time and have them reversed. See what I mean? And as it turns out, we can do that. And so, and let me ask you a question. Is this tail recursive? This my reverse? No, why not? What do you see about that makes it not tail recursive?
Save all the add to ends all the way up.
Well, right, and because yeah, can you point to the code that makes it not tail recursive?
Add to end.
Yeah, add to end. After we call my reverse, we have to do add to end to that. Yeah. So the way to make this big theta of n
by making this big theta of n, the way we're going to do it is we're going to do it by writing a tail recursive version. Now, so how, remember what's the principle of making a tail recursive, of making a recursive function tail recursive, and or what our author calls iterative?
Helper function?
A helper function. And usually, well, how many parameters does a helper function have compared to the original function?
One more. than the original.
Usually one more, right? And so now, instead of, and how many parameters does reverse have? Here, how many parameters does reverse have? How many parameters does reverse have?
2.
How many parameters does reverse have?
1.
That's what I thought you said. Yeah, it's add to end is what has 2, but reverse only has 1, right? Okay, so if we're going to write a tail recursive version of reverse, how many parameters should it have, do you think? I mean, usually according to our pattern.
2.
It should have 2. Now look, so the helper function is going to be reverse onto. We're going to call it reverse onto. And here's what it's going to do. Here's an example of how reverse onto works. If we say reverse onto, and we have these 2 parameters, each one of them is a list, and the first list is A, B, C, and the second list is 1, 2, 3, what is reverse onto going to do?
Reverse the first and reverse the second.
Yeah, it's going to reverse the first one, but it's going to put it what? Onto the second one. Do you see what I mean? Now look, can you guys see this idea? Can you see now that this is going to be how we get this in big theta of n? Let's just think about this for a minute. Because look, how can you peel this one element at a time onto this? In other words, how, if we have A, B, C, and 1, 2, 3, how can we do it one step at a time? How can we make progress? How can we make progress starting with A, B, C, and 1, 2, 3 onto here? Look. Now look. What's the car of A, B, C? A. And what's the cooter of A, B, C? B, C. So now, can you see? What's the next thing to see? If you did the reverse onto of what? Can somebody see where we're heading? Can you see where we're heading? What we're heading? If you do the reverse onto of what with what?
B, C, and A.
No. Because look, here, not B, C, and A, but you're close. You're halfway there. Close but no cigar. Somebody told me where that phrase came from.
So it sticks the reverse of the first part onto the second part?
Yeah, exactly. That's exactly what it does. And what I'm saying is, do you see that the car of ABC is A and the cooter of ABC is BC? So what would you do? What would you do with the BC? How would you call reverse onto? Does anybody see it yet?
The car on
You,
Rest. Yeah.
you cons a
Reverse onto
you reverse onto, yes. You reverse onto
BC.
BC onto the 1, 2, 3, and then what? So here, if you, well, yeah, I take that back. If you cons A onto the 1, 2, 3, then that's the A 1, 2, 3, and then what do you do with that?
cons reverse onto BC.
That's the
You
small
just,
one.
no, you just do what?
You reverse onto.
You reverse onto, yes. So you reverse onto what?
BC.
BC, yeah? So here, so you reverse onto BC onto the A123, and that will give you the CBA123. Now, does everybody see how that worked? Okay. And look, the reverse onto of ABC and 1, 2, 3 is, when it makes the recursive call, what's it going to do? It's going to reverse onto BC of A1, 2, 3. So will that be tail recursive? Because the reverse onto will just be the what? The reverse onto of these two lists will be the what? The reverse onto of what? Of these two lists, right? So you can see that reverse onto we'll just call reverse onto. And what's the base case?
Empty.
Yeah, which one being empty?
First word.
The first one being empty. And then when the first one is empty, what do you return?
The second one.
The second one. Does everybody see how that would work? So remember, reverse onto ABC 1, 2, 3 does this. So we define reverse onto, and it takes two parameters, ABC and 1, 2, 3, in this example. And so we'll call those list 1 and list 2. So define reverse onto, lambda, list 1, list 2. Okay, what did you say the base case was?
Empty. No.
Null. Okay, so the next line will be what?
No. This one.
If null list 1, right? And in that case, what do you return?
This two.
Ah, very good. Otherwise, what do you return? The reverse onto of the what? The cdr of the list 1 and the what? Now, can you write this? Can you code this?
Cons.
The cons of the
Car.
car of the list 1
Equals two.
with list 2. So the cons of the car of list 1 with list 2. Good. Now that's the helper. How is the, oh actually, what is the big theta of this? Yeah, so what is the efficiency of reverse onto? And why is it n? Because it just, it's actually, it's n, oh that's a good point. It's n where n is the length of list 1, right? Because the list 1 is what goes down. So list 2 could be whatever. And in fact, so it's big theta of n, where n is the number of elements in list 1. And now you guys, what is reverse? Now we'll call it your reverse. So now what is the code for your reverse? What will it do? How will your reverse use the helper reverse onto? It's just one call. And what is it? Yeah, and so can you define here? So efficient version of reverse. Define your reverse, and how many parameters does your reverse have? 1. And now here's why I couldn't demo reverse onto, because guess where we're going to define reverse onto? In. Yes. In your reverse. So, boom. There's the reverse onto. Are you with me? And now this paren matches this define reverse onto. So from here to here, that's defining reverse onto, which we just did. And see, I couldn't type it in because it's hidden. You see what I mean? I couldn't demo reverse onto because it's hidden. And now, but after this definition, what's the call down here now? With these, what's the call down here? Reverse onto what? List and the empty list. Good. Is that slick? And that's our more efficient version of reverse. And by the way, reverse, there is a reverse that's built in. That's why we had to call it my reverse and your reverse, because reverse is built in. But that made for a great exercise.
Can you still call reverse onto by itself if you want?
No, because the definition is hidden. It's the scope of that definition is inside the your reverse. That's why I couldn't. Even if I define your reverse this way, and I try to call reverse onto, it will say undefined.
Which means we can use the word reverse onto again later if we want to make that a separate definition of its own.
We could,
Okay.
yeah, yeah. All right. So, okay, so here's our demo. And check this out, sports fans. Define palindrome. Now, you guys know what a palindrome is?
Man, plan, canal, panel.
Oh, you have a whole list of palindromes. Definition by example. What are they? Wait.
The word is the same.
The word is the same backward as forward. Yeah, like radar. What are those ones that you said?
Well, that's one. It's a man, a plan, a canal, Panama.
Ooh, I haven't heard that one before. Say it again.
A man, a plan,
A man, a
a
plan,
canal, Panama.
a canal, Panama. Whoa, that's got to be. I wonder if there's some record for and correct grammatical English sentence for that's a palindrome. Yeah, you probably Google it now. Okay, so check this out. Palindrome. I don't think I'll type your whole thing. I'm going to do RADAR, and that's true. All right. Now, in order to write palindrome, let's do a few little. Let's do something. Check this out. We know how equals works, right? If we say equals 4, if we say equals 4, that's true. And if we say equals 4 or 5, that's false. But here's the problem with equals. If we say equals, quote, ABC, quote, ABC, do you know what's going to happen here? I mean, why am I setting it up like this? Yeah, it's an error because it expected a number. Equals is for numbers, okay? So that's not so hot. But fortunately, we have a predicate called equal. Equal. That works for lists. A, B, C, quote, A, B, C. And that is true. And we can, it doesn't matter whether it's equal, quote, A, B, C, quote, A, X, C. Okay, so if one of the items is different, they're not equal. And it also doesn't even matter, oops, if one of them equal, if I can spell it right, if one of them is A, B, C, and the other one is, oops, and the other one is A, B. Are these equal? Are these lists equal?
No.
No. And so it doesn't, I mean, it even takes into account. All right, and so now check this out. What is palindrome? So palindrome, so if we do palindrome ABCBA, is that a palindrome? It is. And if we do palindrome, let's do this little group. Is that a palindrome? It is, right? Because it doesn't matter if it has even or odd, right? Number of letters. Okay. So anyway, so how can we define palindrome?
Equal, reverse, list 2, list 1.
Well, but it's list. There's only one parameter in palindrome.
Oh, okay. They cut it in half and then do that?
Well, yeah. And because our reverse is and so is there any base case at all or what? I'm just asking, is there any base case, yes or no?
Yes.
Because it's not recursively calling itself.
Right. Palindrome isn't calling palindrome. Palindrome is just calling. And so what's the one-liner?
Equal.
Equals reverse. If list equals reverse. Oh, you
Oh, you want to if? Do you want to say if equals reverse?
equals.
Yeah, but that would be redundant, right? You could say if equals true, otherwise false, but that's redundant. So the cleaner code is what?
Equal
E-
list. Reverse list.
Yeah, there you go. Equal list, reverse list. Boom. Pretty slick, huh? Okay, now, next topic is, now you guys in data structures, we've done merge sort, right? Watch this. Let's do merge sort, and we're going to merge sort 1933634. 1193. No, sorry. 1933634. 1933634. Now this particular version of merge sort that we're going to do, it has an interesting feature. What do you suppose this is going to return?
1, 3, 3, 3, 4.
Yeah, well, you would think that, but what does it look like it does with duplicates?
Oh, it takes them out.
Yeah, it takes them out. So if it finds a duplicate, it's a little bit more than merge sort. It's a merge and remove duplicate sort. You know, 2 for the price of 1. Is everybody with me on this? Okay, so that's just the way our author decides to program his merge sort. You could do it keeping the duplicates, and it would. Oh well, or could you? That's a good question. This has to do with stability. Yeah. Anyway, let's not go there. Maybe we'll talk about that later. So this merge sort does remove duplicates. Okay. Now, what is the base operation of merge sort? Remember when we studied these sorting techniques in data structures? What do you do? What's the general taxonomy? I mean, what's the general way to sort? You split, you sort the sub, and then you join. And then remember, what's the big thing with the merge sort? Is it in the split? Is the work in the split, or is the work done in the join? It's done in the join. So, and the join is, what our join is going to be called is, it's going to be called merge. So check this out. Now, when you merge two lists, what do you assume, how do you assume what's the precondition? Each one is what? Is already sorted, right? Okay, so you merge, and let's do something like 2, 4, 6, 8, and we'll merge that with 1, 3, 5, 8, 9. 1, 3, 5, 8, 9. And now, everybody sees that 2, 4, 6, and 8 are in order, and 1, 3, 5, 8, 9 are in order, right? So, what do you suppose is going to come out? What do you suppose is going to come out?
1, 2, 3, 4, 5, 6, 7.
But what about the 8? What about the 8s?
There'll only be 1 8.
Yeah, there will only be 1 8. Okay? Because we had an 8 in the left and 8. All right, is everybody good? Okay. So that's how, so that filtering out the duplicates is going to take place in the merge. Does everybody see how that works? Okay, so how in the world are we going to merge? Oh, I'm glad you asked. So look, how are we going to write merge? Now, this is really cool. So we're going to merge 2, 4, 6, 8 and 1, 3, 5, 8, 9, and we're going to get 1, 2, 3, 4, 5, 6, 8, 9. Now check this out, you guys. What do we have to compare to do the merge? What is the car of the 2, 4, 6, 8? That's the 2, right? And what's the other thing we have to extract? The what? The 1, which is the what of the what? The car of the second list. So the car of the first list is 2, and the car of the second list is 1, right? And by the way, if either one of those lists is empty, it doesn't have a car, right? So what's the base case? If the first list is empty, what do?
Return second.
Return the second list. If the second list is empty, what do we do? Return the first list. Otherwise, we know that each one has a car. We know that each one has a car, and we also know that each one has a cooter, right? Each one has a car and a cooter. Okay, so the car of the first list is 2, the car of the second list is 1. And what do we do? And what do we do at this point?
Compare them.
We compare them, once we know that each one of them has a car. And now, you guys, which one is smaller?
One.
The 1. So how do we recursively, so what do we look at now? The 1 is smaller. So now, are we in the functional paradigm now, this way of thinking about functions? What do we, does anybody have any ideas?
Cons 1. And then
Yes. We're going to cons the 1, but now what are we going to be working with? We cons the 1, but what do we cons it with?
merge
We merge. Yeah, what do we merge?
list 1.
We merge list 1, but we merge list 1 with the what? With the cooter of list 2. So the cooter of list 2 is 3589, right? Are you with me? The cooter of list 2 is 3589. So yeah. So now, so what do we merge? So we merge. So what 2 lists do we merge? We merge what? The 2468 with the what? With the 3589, and that's a recursive call, and one of those lists is shorter than the original, so we're making progress towards the base case. Are you with me? So we merge the 2468 with the 3589. That's going to give us what? 2435689, and it's, yeah. And as all we have to do with this is what?
Con
Cons the what?
1.
The 1, yeah.
Car.
So yeah, so we yeah. Now, so look, so can you say this? Can you say what gets returned in this situation? We return the what?
Con
The cons
of
of the
car
car of
of list 2.
list. Oh yes,
Yeah.
yes. We do the cons of the car of list 2 with the what?
Merge
With the merge
list 1, cooter
of the list 1 and the
cooter of list.
cooter of list 2. It's all you just say it. You just see it and you say it and then you type it. That's pretty cool. That's pretty nice. Okay.
How does it get rid of the duplicate?
Oh, notice that what will happen is you will compare. Yeah, we'll see how that happens in the code. But what we'll do is we'll compare the car of this with the car of this, and if they're the same, that's when the code will not do one or the other. If they're the same, it'll just, you'll see. You see what I mean? But what happened here, they were different. The way it detects duplicates is when it compares the car of list 1 with the car of list 2. Is everybody with me on this? Okay, so let's see if we can write the code. Let's go back to our demo, and let's see. Oh, this is merge sort first. Haha. Okay, rats. I wanted to walk us through merge before doing merge sort, but we'll do merge sort because that's what's coming up next in the list. So now, let's think about how to do merge sort. How many parameters does merge sort have? 1. So what do we have? Right. Lambda list. Okay, now, what are we going to have to do? Actually, this will be good. We'll take a look at the top level of merge sort. Now, what's the first thing you have to do with merge sort? Remember how that worked from our, yeah, you have to split it in half. So here's how we're going to split it in half. Well, actually, it has a base case, right? If it's empty, what do we return? If the list is empty, what do we return? What do we return if the list is empty? The empty list. Good. Okay. So there's our first condition. Okay. Our next condition is what?
One element.
One element list. So how do you check if there's a one? Oh, didn't you have to do this for your maximum function? I think you had to do this for your maximum function, didn't you? Because in order for a list to have a maximum, there has to be at least one element in it, right? Okay, so the way you check to see if it has at least one element is you check to see if the cdr is null. Okay, so now, if the cdr of the list is null, what do we return? Well, we don't return the car of the list because,
Return the list.
yeah, we can return the list, yeah, okay. The reason we couldn't return the car of the list is because the car of the list is an element, we'd have to return the list, okay? Okay, so now we know it has at least two elements in it. So now what do we do? So now else, here's what we're going to do. We're going to do merge, we're going to merge the what? Now what is this, can you see what this does? We're going to merge the what? The two halves of the list. So, but we have to recursively sort the two halves of the list before, right? So we're going to merge the merge sort of one part list with what? Merge sort of what? Some second part, yeah. We're going to call it the other part. Okay, so our author calls it the other part. And then there's our merge sort. And of course, later we will show how to write one part and the other part. Okay? Is everybody good? All right. So now let's see. Now let's define merge according to our slide. According to what we saw on the slide. So how many parameters does merge have? Two. So there's a list 1 and a list 2. All right. And so if our first condition is if the first list is empty, what do we return? The second list. And so what's our next condition? Second list is empty, so parentheses, null, what? Null, list 2, list 1. And now we know that each one of them has a car, right? So now, let me ask you. Oh, I should have asked you before I revealed the slide, the line. If the car of the first one is less than the car of the second one. Now, is that the one that we did in the slide? No, I think it was the opposite, the second one. So let's think how we would do this. So if the car of the first is less than the car of the second, what do we return? The car of the first, we cons the car of the first with the merge of the cdr of list 1 and list 2. So we cons the car of list 1 with the merge of the cdr of list 1 and list 2. Isn't that amazing? You can just write this. Do you think this is easier than when we did this in C++? Okay. Okay, otherwise, so if it's less than, we do this. If it's not otherwise, what do we do?
Cons the cars too.
Oh, actually, there's going to be another test. Here's where we're going to eliminate, Danny, you asked about the eliminating the duplicates.
Yes.
Okay, check it out. Now, how are we going to eliminate the duplicates here?
Car.
Can anybody see how we're going to do this? We're going to check if it's, okay, this is less than. What are we going to check next?
Equal.
If it's equal, if it's equal. So if they are equal, now how are we going to? Yeah, cons the car of either one with the what?
Could.
With the what?
Could.
Well, with the merge. Are you with me? Okay, so you cons the car of either one with the what? Yes. Okay, so we cons the car of list 1 with the merge of the cooter of list 1 and the cooter of list 2. So that's how we remove the duplicate. And then what? Else what? Now, can you, else what do we know? We have a trichotomy here, right? If the car of list 1 is not less than and the car of list 1 is not equal to car of list 2, we know it must be greater than. So what? This is the one we did in the slide, right? Else what? Else cons the what? Car of list 2 with the what?
Merge.
Merge of the,
Could have missed 2. Or wait.
well, I think the way to say it would be list 1 with the what? Could have list 2, right? Is everybody good? Okay, now, the next thing is how do we split them in half? Now watch this. This might be a little surprising. Because in C++, when we're dealing with arrays, as opposed to lists in Scheme, we had this index, when we could do mid gets, low plus high divided by 2, right? But here we don't have an index. We're going to do these with lists. So guess how we're going to cut the list in half. Watch this. We're going to do this. We're going to say odd, now watch this, odd part. So what do you suppose the odd part of giraffe is? What do you suppose the odd part of giraffe is?
Oh, A.
No, it's a bunch. It's roughly half of it. But what? Well, would that be the odd or the even?
GRFE.
Yeah, GRFE. Is everybody with me? Yep. And now what? Well, if there's an odd part, there must be a what?
Even part.
So we have even part of GIRAFFE. And what's the even part of this, right? IAF, right? And now what happens is what our author is going to do, what our author has done is he's just made these the same name for some reason. Because what did we have in our merge sort? What did we have? We had one part. So watch. If we do one part, GIRAFE, that's just what? The GRFE. And if we do the, what was it called? The other part? Was that what it was? The other part. Then that's the IF. So, odd part, even part, one part, the other part. Green eggs and ham, whatever. Okay, so here. Now let's take a look. Let's take a look at how we're going to program up odd part. GIRAFFE. That's GRFE. So now how do we now remember this is going to be cool. What's the odd part? Tell me how are we going to peel apart the odd part and the even part here? This is nice.
Would it be cons the car?
Yes. And what is the car? The car is G. Are you with me? And then what other, and then what's the other thing we have to look at? The cutter, well, yeah, now you're wanting to do the cutter of the cutter, but let's just stop at the cutter and think about this. The cutter is what? IRAFFE. But now what do you notice about IRAFFE? If we take the even part of IRAFFE, what do we get? We get RFE. Are you with me? So the only thing we have to do is what? Is cons the G. Yeah? So let's write here. So look. So how do we do the even part? Here. Or sorry, how do we do the odd part? So now define odd part. How many parameters does odd part have? 1, so lambda list. And now, what's the base case?
0, nothing.
Null. If the list is empty, then what is the odd part of it? Nothing. Otherwise, what is it? Otherwise, now what did we say we had to do? Cons the what? The car of the list with what? Cons the car of the list with the even part of the code of the list. All right. And now this is it's kind of interesting. Can you define the even part?
Exactly the opposite.
Well, is it? I guess maybe it is.
Or I guess it would be.
Well, except with the even.
Would it be
No. Wait. No, I don't think it's the same, right?
Cons the car of the cutter of the list.
Because because the odd list includes the first one, but the even one doesn't. So what is the even part? Well, what's the base case? So we have lambda list, and if null list, what do we return? The list. But no, I don't think it's the same as it. What is it? Is it cons?
Odd part of the cutter of the list.
Would it? Whoa.
Would
I
it
don't
just-
have a
would-
slide. Wait, I don't have a slide for this, but look.
It would be the odd part of the cutter of the list.
Yeah. Yeah, the cons anything. Is everybody clear on that? It's the odd part of the cutter of the list. I didn't make a slide for that, but can you see it? Yeah. And so now what is one part? Oh, rats, I gave it away. I should have put this on a different line. What is the definition of one part? Odd part. And what's the definition of the other part? It's just even part. Yeah? Okay. Well, I was hoping to get through a lot more material than that today, but we'll just call it quits because it's time to go. All right. See you guys next time.